supposed to be tech support. Okay, so good evening and welcome to SUNY Oneonta. I'm the college president, Nancy Klanuski, and it's wonderful to see so many people here. It's a really great topic. Now, let me just tell you a little bit about the background of why we're here this evening, and that is we are recognizing the scholarly work, the research work of one of our junior faculty. Tonight it's Devin Castendyk, who received the Siegfried Prize for his work. And we're also here to commemorate a long time and beloved professor, Richard Siegfried, whose wife Alice has made this lecture series and this prize possible. And she'll be speaking a little bit later, but I just want to thank her and have all of you join me in thanking her for her gift that made this possible. Now, you know that at SUNY Oneonta, teaching is really our #1 priority. Increasingly, however, it's very, very important for our faculty to be actively involved in research, scholarship, and creative activity. This is what keeps them up on their discipline. It helps them to push forth the boundaries of their disciplines by creating new knowledge, and it helps them to model good behavior to their students. So we're very, very proud of the research and scholarly work and creative work that our faculty do. I also want to brag a little bit and say that this kind of event is emblematic of the wonderful intellectual life that we have here at SUNY Oneonta, and I'm glad to see that people from the community as well as from the campus are here to appreciate the work that we do here. So I would like to turn the proceedings over to our provost, Dr. Dan Larkin, who will proceed with the rest of the evening. Dr. Larkin.
Thank you, President Klanuski, and thank you all for joining us this evening. The Richard Siegfried Jr. Faculty Prize recognizes the academic achievement on the part of non-tenured faculty. It is most fitting to name the award after a man known for his dedication to principle, a burning concern for justice, and, as the program notes, humanitarian integrity. He was known as well for his dedication to teaching and to his students and colleagues. It is now my pleasure to introduce Mrs. Alice Siegfried. Alice.
Good evening. I'm happy to be here, especially since a week ago, my bicycle and I were intercepted by an opening car door. Well, after a trip by ambulance to the hospital, I was declared unbroken, but bruised and sore. My 2 daughters, my 2 sons, and I are very appreciative of the Junior Faculty Prize and the Student Awards, named in honor of their father and my husband. They were established in 1995 with funds from the Alumni Association, and I think Richard's name was put on the award by some committee. I really didn't have anything to do with it. Now, our family connections are many, and they started 51 years ago when we came here with my husband as junior faculty to join Joseph Elfenbein in the English, Speech, Theater, and Foreign Languages department when there were 3 buildings. One daughter is a graduate of SUCO. Another daughter, who is here tonight, and a son, took classes here. And the other son married a SUCO graduate. And I learned to be a potter by taking courses from Dan Young, first at Old Main and then at the then new Fine Arts Building. You can read a fine summary about Dick in your program, written by a dear colleague, Ed Pixley. And many times in the last 15 years, I have shared stories about Dick. But tonight I just want to say that these awards, I mean, it would come as a big surprise to him, because he was only doing what he only knew how to do, was to be responsible, to do his very best. As a teacher, as a citizen, as a gardener, as a husband, as a father. His garden and the peace sculpture at 67 Church Street are memorials to him, as well as the peace pole in Muller Plaza. Another surprise I had was, and he would have been surprised too, by the number of people attending his memorial service. A friend had anticipated and arranged for the service to be televised to the downstairs of our Unitarian Universalist Church. And it proved to be necessary. People respected him, and they honored his standing up for what he believed and lived. Directing socially conscious plays, producing street theater, organizing peace vigils, trips to Washington, writing letters. Our presentation tonight is very relevant to Dick's concern about the environment, and I look forward to it.
Thank you, Alice. At this time, I'd like to extend my appreciation to the Alumni Association, which has generously provided funding for the student awards presented this evening. In addition, a very special thank you to Alice Siegfried, whose gift to the College at Oneonta Foundation helps fund the Richard Siegfried Jr. Faculty Prize. Tonight, I'm honored to recognize a particularly notable group of student scholars. Each of the students listed on the program earned a grade point average of 3.9 or above during their freshman year at Oneonta or first year as a transfer student. With those present, please come forward as I call your name. Jessica Bailey. Victoria Chafee. Michelle Facio. Andrew Feiner. Austin Fox. Joanna Gallo. Rebecca Gower. Caitlin Halpin. Richard Jaworski. Kelsey Jones. Megan Kane. Joseph Kennedy. Catherine Lawrence. Jacqueline Lewis. Allison Marmot. Anna Mathis. Samantha Mark. Valerie Nagelmeyer. Shane Putnam. Heather Rutkowski. Amy Seibert. Jamie Stahl. Zachary Town. Curtis Walker. Jacqueline Zopp. Ashley Zotter. Now let's give them all a big hand. Now it gives me great pleasure to introduce this year's recipient of the Richard Siegfried Jr. Faculty Prize for Academic Excellence. Dr. Devin Castendyk joined the college at Oneonta Earth Sciences Department in the year 2005, where he teaches courses in geology, hydrogeology, environmental geophysics, the geochemistry of natural waters, and groundwater modeling. Dr. Castendyk earned a master's degree in geology from the University of Utah and a doctorate in environmental sciences from the University of Auckland, New Zealand. He already has accumulated an impressive record of scholarship, including a book currently in press titled Mine Pit Lakes: Characteristics, Predictive Modeling, and Sustainability. Dr. Castendyk's lecture this evening will explore the environmental impacts of historic mining practices and address contemporary strategies employed by the mining industry to clean up historic impacts and to avoid future degradation. The content will span the coal mining industry, the metal mining industry, and the natural gas industry, which is very relevant to contemporary local debates. I have to tell you also that Dr. Castendyk will be leading a group of students this summer to Iceland. And I know also, by the way, that he has assured me, I've talked to him a great deal about this, that he is going to bring me back from Iceland an honest-to-God puffin. And I'm looking forward to that. I'm actually looking forward to how is he ever going to get that through customs. In any case, please join me now in congratulating Dr. Devin Castendyk, recipient of this year's Richard Siegfried Jr. Faculty Prize for Academic Excellence.
Provost Larkin. I really appreciate it. And thank you all for coming tonight. It's kind of dark, drizzly night out, so it's great to see so many familiar faces, particularly my students who are all in the front row making me nervous. That usually doesn't happen. And also my family who've come in from Massachusetts. Thank you for coming. I graduated from Hartwick College in 1996, so it's really nice to be giving what I think is a local presentation on the work that I've been doing for, I guess, the last 13 years. And I guess I'll start off with some of the things that really, really interest me. I'm really interested in the processes of solids reacting with water. And I also happen to be a geologist, which we sometimes call a hard rock scientist. And this mesh of this love for water and rock reactions and this hard rock, well, you know, this kind of says it all, okay? That's me observing water quality, water chemistry in my best hard rock outfit. And by the way, this will be hanging in IRC next year as your Siegfried award. Okay? On the serious side, I have focused my attention on the water quality that exists at mine sites. And I've spent a lot of time looking at various mines in various parts of the world and trying to evaluate the environmental impacts and trying to ask a very simple yet very relevant question. And it really is the focus of tonight's talk. How can a society, our society, meet its current need, and I'll put in parentheses, demand, for water resources, for natural resources, without limiting the water resources of current and future generations? Okay, so that's the topic that I hope to touch on tonight. I'll be going over a brief introduction to our use of resources and where they come from. I'll also be talking about metals in particular, and for metals I'll be asking where do they come from, what are the environmental impacts of acquiring these metals, and can metal use, can metal extraction be sustainable? And then I'll turn our attention to coal and finally natural gas, and I'll try and ask this same set of questions for each resource. And I'll wrap up with some conclusions. So we'll start out with our view here in upstate New York, okay? We have a very unique situation in upstate New York in that most of our resources come from somewhere else, okay? We don't drive to work on a daily basis and drive by a mine site that happens to be providing, I don't know, the iron for our cars or the copper for our wiring. And so from this unique vantage point, we're really removed from the process. We're all familiar with the story about children today that think that milk, where does milk come from? Well, it comes from the grocery store, right? And we kind of chuckle because we see cows all the time. And, you know, we are shocked that kids don't know that milk actually comes from cows. Well, this talk, part of the driving force of this talk is to remind everybody that much of our life, our resources, the heat in this building, has come from the earth, has come from the ground. And we continue to use those resources and probably will in the future. This is what's called the resource baby. I didn't come up with the name, I don't quite like it. But it shows, it tries to capture how many pounds of raw material it takes to support the lifestyle of the average American. And so it kind of breaks down the copper that we use, 1,000 pounds of copper in our lifetime. That largely is going into copper wiring, which is circulating the electricity in this room right now. There's also natural gas, which heats homes, drives electricity. There is, of course, aluminum. Had to put a frying pan in there. Coal. lots of coal that we use for electricity, and everybody's favorite, gold, which we ornament our rings with, our fingers with traditionally. And so if you add up all these things, and there's a lot that I haven't talked about, but the average American uses about 42,719 pounds of earth material per year to sustain our lifestyle. And if you carry that out over a 77-year lifespan, we use about 3.3 million pounds of metals, minerals, fuels within our lifetime. Okay, so what does that equate to? Imagine this room filled all the way up to about 2 feet from the ceiling with solid rock. This entire room. This is a pretty big volume, all right? That's how much each one of us is using in our lifetime of raw earth materials, just by living and building buildings, building roads, buying cell phones. Cell phones, incidentally, have about $1 of gold in them, okay? At least in 2007. Maybe it's a little more now. But everything we use has metals in it. To make the situation even more impressive, this is a plot of global population, we make up this little, we meaning America and Europe and some other developed nations, we make up this tiny little smidgen of the global population. There is a lot more people out there making up this blue portion of the diagram that wish to live the same exact lifestyle that we live. Which means if everybody out there had this large of a footprint, that would be quite an impact. I'm just trying to demonstrate that we use a lot of materials, and we'll come back to that. So where do our minerals come from? Okay, we're going to start off with metals, and for this I'm going to give a little video clip to demonstrate, here we go, to demonstrate some of the mining process. Let's go play and cross our fingers. There we go.
The human race now moves more rock and soil on the surface of the planet than all the Earth's natural processes put together. No species has ever dominated the planet like this. In fact, our influence is now so great that many scientists believe a new geological era has begun. The Anthropocene, the human era.
Okay, so just to kind of get out of that, no we didn't, 1 second here. And hold our breath. Good, we're back. Okay, so that video gave you a little introduction to the mining process. It actually was, for dramatic effect, it was kind of shown in reverse order. The way we really do this is that we drill a bunch of holes in the ground. We fill those holes with an explosive, usually nitroglycerin. We detonate those explosives to make a very large amount of powder and fine-grained rock, which you saw in that movie. And then we bring in our dump trucks, and we scoop up that rock, and we ship it off for refinement. Some of that rock goes to a mill and gets processed to make raw metals. The rest of the rock that we don't use, usually gets distributed at the sides of the mine. Okay? This is the Bingham Copper Mine outside of Salt Lake City, Utah. Just to give you a sense of scale, from this near rim to the far rim is about 2.5 miles. This is 1 mile deep, and it's one of the few man-made objects that can be seen from the space shuttle without the aid of any magnifying objects. These things tend to be big, especially these copper mines. This is quite a large resource here. Another consideration to think about is the price of precious metals. Last week, gold did something it's never done before. It crossed the $1,100 per ounce level. It's the first time in history that gold has been worth that much. And this is a little graph going back to '96. And you can see the price of gold kind of fluctuated, and whoa, right around our housing market crisis, the price of gold went way up. Okay? People view gold and other precious metals as a secure investment during unsafe financial times. And so the price of gold goes up, and of course, this motivates more mining. Okay? So just to bear all that in mind. One of the environmental impacts that I have studied related to mines is a relationship between this little mineral here, pyrite, and water. Pyrite is found in lots of deposits, in coal deposits, as well as most precious metal deposits. And there's a very simple reaction here. When you have pyrite and you add water, you get acid mine drainage. This is basically sulfuric acid, and it also is a slimy form of rust. And you're seeing a slimy form of rust in the bottoms of these streams. And this is, according to the global mining industry, this is the #1 issue, environmental issue that is of concern. And I'll give you a worst case scenario of this. Because of course, when you have this big, huge open pit, and when you have wall rock that has the potential to generate acid, that acidic water can get washed into your pit, and the whole pit fills up with acidic water. This is the Berkeley Lake in Butte, Montana. It has a pH of about 2.5, which is pretty low, but remember, Coca-Cola has a pH of 2.3. So, you know, this is basically a lake full of Coca-Cola. But it also has an elevated amount of copper in it, okay? In fact, 70 times the human drinking water limit for copper. And in 1995, a flock of about 300 Canadian snow geese landed on the lake, and instantaneous, well, about 7 minutes were done in by the water chemistry of this surface. So in my realm, in my work, this is what we try and avoid. And the question then is, can mining be sustainable? How do we as a society meet our demand for copper? Because none of us are actively bringing or giving up our cars or giving up other things to prevent mining. What can we do to make mining more sustainable? And one of the pictures you see here, this is from a mine site in New Zealand. This is an active gold mine. If you were to go right over that rim behind the truck, you would see a 200-meter deep hole in the ground. And yet, they are actively grassing over their mine site, their waste rock piles, and raising cows on these sites. When we talk about sustainability with mining, it's obviously, there's a paradox there. How can you have the sustainability of a resource which is limited? Because we pull it out of the ground at a faster rate than geologic processes reproduce or replace it. However, the mining industry and I have taken the approach that, well, what if we can sustain our land resources, our water resources, our air resources, and our soil resources? If those things can be sustained, then while the mineral concentration may decrease over time, you are at least mining in a way that some of the things that we need for our survival are sustained. And so this is one example of land sustainability being practiced in New Zealand. Here's another favorite example of mine, the Golden Cross mine in New Zealand, before and after rehabilitation. This mine site has now been backfilled, seeded over, and it's now a public park area. This is just one example of how these sites can be reused. And another example, and this is one of my favorite examples because it involves water. Now here is the Island Copper Mine, which is on Vancouver Island on the shore of British Columbia. Okay, if you can imagine that. This is actually an arm of the ocean. This is Rupert Inlet coming into Vancouver Island. And this is a copper mine. So it had the same kind of potential as the Berkeley Copper Mine. Which incidentally, the Berkeley Copper Mine, as much as we go, that's awful, and it is awful, probably given the age of this building, some of the copper at least that's bringing electricity to the lights in this room came from the Berkeley Copper Mine. I would imagine, just given the age of when this building was built and how much copper came out of there. So anyway, shifting our attention to another copper mine, they wanted to limit the environmental impact. They knew they had the potential for something. So what they did was they did a computer program that predicted all of this in advance, the water quality impacts, they breached a wall in the side of the mine and flooded the entire mine. They had one of the largest waterfalls in British Columbia for about 3 days until the mine filled up. But that was seawater. And they did this, well, I'll tell you why they did it in a moment. It's really exciting because they didn't fill it all the way up to the top. They filled it about 30 feet from the top. And they capped off the lake with a layer of fresh water. And just like anybody who's ever noticed their salad dressing separating with the oil and vinegar in different areas of the salad dressing, the same thing happens between fresh water and salt water. And so they've created a lake that permanently cut off the bottom rock layers from oxygen, from the oxidizing impacts of our atmosphere on that pyrite. And today, the water quality, the surface water quality of this lake is still one of the highest of any pit lakes of this kind. I think they might even be putting fish into it, but I have to double check on that. So this is one of the, in terms of pit mines and pit lakes, this is what I consider a success story. And it's one of the, it's motivated a lot of mining industries to move in this direction. So where are we going to get our resources tomorrow? What happens when these mine sites are pretty much expired? Well, right now we throw away a lot of rock that still has metal in it, still has copper, it still has gold, but right now it's not economical to extract those metals out. And chances are, in fact, the prevalent theory is that the mine sites, the mine dumps of today are going to be the mine sites of tomorrow, once it's economically profitable to go back to these areas and keep getting resources. That requires a heck of a lot of energy. Okay, so I'll segue into the next part of my talk here and talk about our energy resources. Now, in the United States as a whole, if we just look at our electricity supply, 49% of our electricity as a nation comes from coal. Another 21% comes from natural gas, and 19% comes from nuclear power. If you put all that together, that means 89% of the electricity used in the United States has been mined. It's come out of the ground. Okay? Let's ask the question, where does this come from? Well, coal is generated very much the way copper is generated, from large-scale open pit mines. This mine is in Canada. And yes, there are local impacts. Again, acid mine drainage. This is a shot of mountaintop removal in West Virginia, an aerial shot of that. Obviously, changing the view of the landscape, changing drainages. I'll briefly touch on these. Fly ash disposal and lung disease are also have been associated with coal and coal use. There's another impact that we don't talk about, I think we don't talk about enough, and that's mercury. We have, this map is showing mercury wet deposition, meaning mercury deposition in rainwater across the United States. And you can see New York, we're not in this really, really green zone. We're more in a kind of beige and down towards New York City, an orangey zone. I know you can't read the graph on this. It basically gets higher concentrations as we go down. And the take-home lesson here is we receive mercury in our water as a function of, I believe, as a function of coal and coal burning. In fact, we receive so much so that our lakes and rivers locally have health advisories about the amount of fish that we can eat out of these rivers. Goodyear Lake, the Susquehanna River, the Unadilla River, all of which have health advisories that go as follows. An adult should not eat more than 1/2 pound of a 22-inch walleye per month. Now, if you are a female of childbearing age, meaning half the population of our campus, you shouldn't eat any fish from this river. If you are an infant or under the age of 15, you shouldn't eat any fish from these water bodies. Okay, people are very concerned about local water quality impacts, and this is something that has really just been brought to my attention. This is a document by the New York State Department of Health published this year So this is not historic data. These are actual advisories in effect right now about what should be eaten out of our local rivers, and that's coming from mercury. And then, of course, there's the issue that we're all familiar with, global warming. I won't touch on this because I think it's been covered very well elsewhere, but it is directly related to the amount of coal that we burn on a national basis. So can coal be sustainable? I saw a talk by a member of the coal mining industry about a month ago, and I was very enlightened to hear a representative of the coal mining industry saying, yes, we are generating a sea level rise problem. We are causing global warming right now. And I was like, wow, a member of the coal industry is taking this on and acknowledging this. And in the coal industry's mind, there is an option, clean coal technology. Okay? It goes something like this. First, practice sustainable mining. So avoid the acid mine drainage impacts that I was talking about. Next, figure out technology, and I say figure out because we're not there yet, to remove mercury from the emissions, to remove sulfur dioxide and nitrogen dioxide. These are the components of acid rain. Remove those from our emissions, and also carbon capture and carbon sequestration. Now, carbon capture is the idea, essentially, that you're going to put a vacuum cleaner of some type on the side of your coal power plants and remove selectively the carbon dioxide that's being produced. You then need to supercool that carbon dioxide, which of course requires a bit more electricity, but we supercool it till the carbon dioxide acts as a dense, almost like a fluid. It's not exactly a liquid at that point, but it acts, its volume gets shrunk down and it acts more like a fluid than it does a gas. And finally, carbon sequestration. The idea of carbon sequestration being that we're finding very deep, deep rock layers to inject this super cooled carbon dioxide down into. And this representative of the coal industry effectively told me that we have the technology to do this today. Some states, and New York is not one of them, some states have already permitted carbon sequestration drilling to occur. And so this is going to be happening in some places. In the coal industry's mind, we have about 150 years left of coal to sustain our current demand for electricity. And they're arguing that carbon sequestration is the way forward. If we want to avoid global warming or sea level rise, carbon sequestration can bring our society through this. Again, that's the stance of the coal mining industry. So let's take a look at New York now. This is a map showing our power supply. The black triangles stand for coal mine power plants. The red circles stand for nuclear power plants. The blue diamonds represent hydropower, and the upside down triangles represent natural gas power plants. We are very fortunate in the state of New York. We have the largest hydroelectrical power facility east of the Rocky Mountains, and that is at Niagara, the Moss Niagara hydropower plant. But we also have our fair share of coal power plants, as you can see by these black triangles. And in fact, I am guessing, given the proximity between here and Binghamton, that the electricity powering this presentation in this room right now, and I can't guarantee this, but just proximity based, I think it's coming from this power plant, which is a coal burning power plant in Johnson City, right outside of Binghamton. So that's where our power is coming from right now, from coal. What else do we have in New York? Well, one thing that immediately leaps to your mind are all of these orange triangles. These are all natural gas-fired power plants. And in fact, when we look at the electricity being produced in New York State, 34% of our electricity is coming from natural gas. Another 33% is coming from nuclear power. 9% is coming from coal, and 20% from hydroelectric. This is where we're getting our electricity right now. not only are we using natural gas for electricity, but about 52% of the state, myself included, is going to use natural gas to heat their homes tonight. Okay? The other percentage comes from fuel oil, a little bit from electricity, which goes back to the coal. But this is how we're heating our homes, using natural gas in general. So here is the question, where does natural gas come from? Here's a drill rig. This is some of my students from my intro hydro class. And this is in Maryland, New York, earlier this year. This is a vertical well. Let's take a look at where natural gas comes from. We have, in our area, a type of natural gas called shale gas. And this is gas found in very deep shale layers. And we have two prominent shale layers in our neighborhood, the Marcellus and the Utica shale. It's difficult to get gas out of these deposits. In fact, it requires a bit of coercion in that we have to pump water down into the wells, fracture the rock, and by fracturing the rock, it stimulates gas flowing into the well. Traditional wells, like the one I just showed, usually are vertical wells. And vertical wells, they work in these settings, but they don't produce an enormous amount of gas. Within the past 10 years in Texas, in another shale-bearing gas unit, they have found that this technique of horizontal drilling essentially just allows for a lot more contact between the rock and the well hole. And so you end up getting a lot more gas out of this process, this horizontal drilling. And that's the technology that's been proposed for upstate New York. Now, a lot of us have heard about impacts related to natural gas drilling. And I'm not going to spend a lot of time talking about these. I'll talk about some of the ones that relate to my field in that people are concerned about decreases in surface water volume. This hydrofracturing, this breaking of the ground, requires a lot of water. So we're concerned about that. We're concerned about fluids from the drilling site somehow getting into our drinking water supply. And we're concerned about things like methane in drinking water supply. There's a lot of concerns that are going around our community. I think a lot of people are probably familiar with these. So how do we address this? How do we ask that same question that I've been asking? Is drilling sustainable? How can we make it sustainable? One of the best ways to handle an issue like this, especially when we don't have existing examples in New York State of wells, well, one of the best ways to look and see what's happening in other states. But another good way is to perform what's called a risk assessment. Okay, we start by by taking those problems that I just listed and by first ranking the severity of each problem. Okay, what's the worst possible thing that could happen? And I've ranked that number 10 as being loss of human life. I think we'd probably all agree that of anything that was up there, loss of human life, if it could somehow happen, would be the worst thing there. And next would be impairment of health, next destruction of an ecosystem, and probably working our way down. Okay? Everybody has different priorities, so your list of severity might be different from my list of severity. But we first rank things in terms of what would the result or the magnitude of that impact be. The second thing is that we rank the probability. Now, we deal with probabilities all the time. Everybody's walked down the road. In fact, you'll go to your car tonight through a rain situation. There's clouds up there. And I suppose there would be an ability, a probability, a very small risk that we could get hit by lightning. Okay? That would be near the 0 probability scale. Whereas there would be 100% probability if you were to dress completely in black, put on a blindfold, and run out in the middle of I-88 at the middle of night. Okay? If there'd be a huge probability that you'd be hit by a car, say. Okay? That's the difference between this probability scale. When we start breaking down our list of concerns and plotting them onto this kind of a graph, it helps us to make sense, to identify what are the biggest problems that we need to be addressing. Now, this is not what I would call a quantitative risk assessment at all. I don't know what the numbers exactly are. I'm just going on what I've heard from others. And so I assembled this diagram. Don't take it literally. That's what I'm trying to say. But when we do this for our concerns for drilling, we find that, yes, drilling fluids getting into our public water supply or our personal water supply would be, a very severe impact. That would be something that we're very concerned about. However, the probability of that happening is very, very, very small. We have drilled a lot of wells of this type in the country, and very few of them end up having this type of problem. And you can go through and rank other problems in the same exact sort of way. And you come up with a couple of different boxes. You have your high severity, low probability. You have your low severity, high probability, such as we might probably see more traffic in this area. That is going to have a very high probability. It is an outcome that will result from drilling. Another thing, since I'll mention it to this audience, there's probably a high probability that come graduation time, there might be no vacancy in our hotels, which could be a problem, okay? So that's a ranking of some of our concerns. And obviously the things we're most concerned with fall into this red box right here. Now, once we identify our concerns, the beauty of a risk assessment is that you can actively look for ways to say, all right, what are we going to do to prevent this very high probability or very high severity issue from happening? What can we actively do to prevent that? And we can also say, all right, well, what if the worst case scenario did happen? What are we going to do in the event that one of these awful things happens? By working on prevention, we reduce the probability even further. By working on a response action plan, we reduce the severity. And so we start to minimize our risk through a risk assessment. Now, I will mention this. Part of risk assessment involves oversight. It involves making sure that the right stuff is going on. And in some areas, lack of oversight, and we've seen this perhaps with our economy recently, lack of oversight increases the probability of something bad happening, okay? I mention this because our state regulators are committed right now. They're saying we are going to inspect every single site. Well, that's very similar to what the Pennsylvania state regulators were saying. And in Pennsylvania, there was, if I have my facts straight, what happened was they were inspecting every single site, but that takes a long time. And the landowners were getting restless. They wanted to start seeing some revenue come in. And so a lot of pressure was placed on the state government to accelerate the process. The state government, in turn, came back to the regulators and said, well, can we move this along a little bit? And according to some friends of mine that are now water regulators in the state of Pennsylvania, they've gone to more of a rubber stamping approach in Pennsylvania. And under that circumstance, you're increasing, possibly, the probability of something bad happening. So oversight, it's an important part of this process. All right, wrap all this up. In conclusion, I think it's important for all of us to recognize where our resources come from. In order to really minimize our impact, it's important to know where copper comes from. Where do the metals in my cell phone come from? My computer. It's important to understand these things in order to preserve our future resources. Strategies do exist to minimize the impacts of mining resource acquisition on land, soil, and water. And we need to keep asking, is this sustainable in the long run? As our human population rises, and this is really where things start hitting home, there's going to be demand for new supplies. And hopefully through risk assessment, we can minimize both the severity and the impact of these issues. I'll leave you with one further slide, and that is, where will our future energy come from locally? I've lived here 4 years now, and in my 4 years, I have seen opposition to, in fact, I even participated in the opposition, to a wood power plant that was going to be in Oneonta. There's also been a plan to put in windmills in Cherry Valley, New York. That also got shot down. And now we are dealing with issues regarding natural gas. And you can see some of those flyers there. I'm not sure which energy approach is appropriate for Oneonta in the future. But one thing's for sure, we are using a lot of electricity and a lot of resources. And I think we need to shift some of our local debate, not only from what we don't want to see, but what we do want to see in our area. Because right now, the status quo is more coal, and I can tell you that the nuclear industry is already gearing up for more nuclear power. So if we want to see alternative resources in our area, we need to start coming up with solutions. We need to consider the true impacts of some of these resources that we have available. And at that, I'll say thank you very much and answer any questions you have. Yeah. No questions? Ah, okay.
Is CO2 the major component as greenhouse gas?
Well, it is, where's Todd? Todd, correct me if I'm wrong, okay? CO2 is actually the most abundant greenhouse gas that we have on this planet is water, okay? That's the most abundant greenhouse gas because it traps energy. Carbon dioxide is also a very efficient trapper of energy, and we have a lot of it in the atmosphere. Methane is even more efficient at trapping energy than carbon dioxide, but we don't have, fortunately at this point, very much of it in our atmosphere right now.
Okay. And you said SO4?
SO2,
Oh,
yeah.
SO2.
It's basically that pyrite that I showed a sample of that also exists in coal. When you burn that in a coal power plant, you put that sulfur into the atmosphere. And just like you can have acid mine drainage in a mine site, reacting sulfur with water, when you put that sulfur into the atmosphere, it reacts with water, and that's where we get our acid rain from in this part of the world.
And that has an effect that's not necessarily local, because once that gets into the atmosphere, it spreads to other states.
It does.
And so legislation in one state
Exactly.
affects another state.
You're dealing with an interstate environmental impact there. Yeah, definitely, good point. Wendy?
Kevin, you talked about the clean coal technology and kind of the coal industry's view on it, right?
Yes.
What's your opinion? Is it a viable, sustainable option, quote-unquote sustainable? What's your opinion?
I imagine it's a lot better than what we're currently doing. And
Is it really the way we should be going?
no, I think I would like to see, in fact, with all of these, I'd like to see a trial run of it. You know, I'd like to, I'm always of the go slowly approach, but go. You know, try it, monitor it, you know, have everybody watching what's going on, because, you know, it might be a viable technology. I do know there are problems with it, though. You're injecting water down into very salty aquifers, and once you're pushing new fluid into where old fluid currently exists, that old fluid starts moving. And so some of the problems or some of the issues that we have, or concerns that we have locally with natural gas also, I think, apply to this carbon sequestration technology, because they both involve injecting fluids at depth and them going somewhere. But I think, you know, small-scale pilot studies are perhaps the way to go, to at least see, you know, what can happen. Yeah, in the back, Chris.
What are some of the other arguments against harnessing wind energy other than just unsightly?
I might be the wrong person to ask for that. Yeah, Allison?
Well, it's about the birds.
Yeah.
Especially the bird habitat.
I have heard of bird impacts, and in our area, I think I've also heard about bat impacts. Yeah, because they can't see or sense those. But I've also heard other stories saying that that actually may not be a huge, yes, it has an impact, big impact if you're a bird, but it may be less than, I'm not sure exactly, yeah. Yeah,
Two things about the windmills. What I've heard is that the bird impact was very large when they would nest in the lattice type towers that they had. But
Oh.
now that there are pylon types, they don't nest there, and so it's way reduced.
okay.
Also, a question about the coal sequestering. Have they ever tried injecting that dry ice that you talked about? Because when it gets warm down there, what's going to happen to that?
Yeah, it'll expand. I think they're trying to inject it, not, they're only going a couple of kilometers down, and the temperature isn't as warm as, it could be if you went tens of kilometers down. But that's a really good point. That's actually one of the questions I had when thinking about it as well. The possibility for expansion. But you got to remember, it's also under an enormous amount of pressure, and it's possible. You can take a 2-liter soda bottle and warm it up. Of course, if you warm it up too far, it will explode. But it's possible that the pressure is great enough to keep that in place. But it's something I have been planning to learn a bit more about the carbon sequestration for that question too. Good question. Todd and then Jerry, yeah.
So I'm wondering, of all the different mining operations to produce, this limited to the energy debate, maybe mining for coal, mining for natural gas, mining for uranium maybe.
Yep.
Is there one of those resources that tends to produce more polluted lake waters than the other? Or has that even been looked at? Sorry, I didn't mean it to be a toughie.
No, it really, I want to give you my stock answer, and that is every single mine site is different. And we don't have generic environmental impact statements for mine sites because they are so radically different. One mine, it's because the deposition of pyrite, which is the major culprit, varies from spot to spot, and you get high concentrations and low concentrations. The people I work with have been emphasizing the management of sites, and is it possible if you manage even something like the Berkeley copper mine, if you managed it differently, could the water have been better? Now, copper is a really good bad example because it seems that no matter where we get copper out of the ground, we produce mines like that. Which is why it's my favorite showcase bad example. But that's actually, on a global sense, rather rare if you compare all the mines. But I guess, now that I mention it, I would say copper is probably, it definitely has a big impact on the water. There's just, it's hard to control that much sulfide material that's in the ground.
Thanks.
Yeah, Jerry.
Last month, I heard a talk by the Secretary of Energy, U.S. Secretary of Energy, in which he indicated that they're interested in expanding our nuclear facilities. That we haven't built a new nuclear power plant in 30 years.
Yes.
Isn't that going to require more uranium mining? Is that a particularly bad type of mining?
I don't think it's particularly bad. I've been to old uranium mines in Utah, and I think my understanding of uranium is that you really have to process it down for it to become something that's really bad for our health. You're right. I was talking with people in the mining industry earlier this week, and they were talking about how their area is ramping up for uranium production, in part because we're not adopting these other resources that are out there. We have a huge demand for energy, and if we're not using, say, natural gas to produce electricity, it's got to come from somewhere. So they're ramping up uranium. They're ramping up other aspects. And yep.
Any recent improvements in how we deal with the waste from nuclear reactors or recycling and some other things?
Not that I am aware of. I still think that the idea, Yucca Mountain, which you've probably heard about in your classes, was meant to be the national nuclear waste storage facility in a mountain in the middle of nowhere in Nevada. And they were talking about that when I was an undergrad 13 years ago, and it still is not open. We're still not putting spent nuclear waste in there. I haven't followed that debate really closely, but as far as I know, we don't have a place to put nuclear waste yet, and we're just currently putting it in temporary stockpiles.